Yeah.
So this is for the problem set, but I'm not gonna ask like directly about the problem. Like, could you just go through like conceptually the idea of like drag force on a and like
So
friction?
drag force.
There's one problem with a skier going down a slope with like a 40 degree incline, and then like friction is pulling them back, and gravity's like
The friction is in the form of drag, right? You're saying?
Yeah, there's actual kinetic friction.
And then there's drag also? Sure.
Gravity.
Yep. All right, so this is the classic problem you see where it's an incline, but in addition to the force of friction itself, you get the force of drag. So the body would look like this. You would have friction going back, FFK. You would have drag force going back, FD. You would have normal force here. You would have FG sine theta here, because we switched the x and y components on an inclined plane. And we would have FG cosine theta. Now, after this point, you would approach it the same exact way, except that for FD, either you have to be given the value, or you have to be given some characteristic. Or maybe you're trying to find the K value from the 1/2 kV squared, or whatever it is. So do you recall what it gave FD as, or do you recall what problem it was at least?
I think you're trying to I know the problem. This problem, I think, 40 of...
Oh, this is from section 6.3 in the homework.
Yeah.
Got it. Hold on, I have a textbook right here.
40 of
Let me just see what it says.
Oh, I have it up right here.
You got it? Yeah, you want to read
It
it?
says at downhill speed, skiing, the skier is retarded both by the air drag force on the body and the kinetic frictional force on the skis. Suppose the slope angle is 40 degrees. Snow is dry snow with a coefficient of kinetic friction of 0.04. The mass of the skier and equipment is 85 kilograms. The cross-sectional area of the skier is 1.3 meters squared. The drag coefficient is 0.15 and the air density is 1.2 kilograms per meter.
Sorry, drag coefficient is what?
0.15.
Was that K did we use? What did we use for that?
See,
C? Thank you.
there's a lot of stuff in this.
Yeah.
And what was the last part after the drag coefficient?
Air density is 1.2
And that's
kilograms
per cubic meter?
Yeah.
And is C a unitless coefficient?
Yeah.
Yeah.
Okay.
Just the
Right.
lump coefficient.
Lumped coefficient. Okay. So in this problem here, we're looking at the fact that the drag force has to be calculated from these three. That's the only part that makes this different than a friction problem normally. So you still have your force of friction acting in the negative direction, FD in the negative direction. So when I look at this problem, I would consider down the ramp to be the positive x. I would consider out of the ramp to be the positive y. My equations would therefore become the following. It would be FG sine theta, this is the x direction I'm looking at right now, minus FFK minus FD equals, or given an acceleration, or is it constant velocity?
It doesn't say.
What are we solving for?
What is the terminal speed?
Oh, terminal speed. Okay, nice. Okay. So we're looking in this problem to figure out what the speed of the object gets up to when its drag force fully balances the weight pulling down. Well, technically, when the drag and the force of friction balance it. So if it's a terminal velocity, when you reach terminal velocity, what must you conclude?
Acceleration is 0.
Is that clear? Why? Somebody else. Why is acceleration 0 when you reach terminal velocity? It's really important that we recognize this. We have to know why it's 0.
Because it's like the max the air can push back on the object.
And therefore,
It's as fast as it can go.
it can't go any faster than that. So it's not going to get any faster. It's not going to just slow down suddenly because the air resistance can't push back any harder than it is already. So this means that MA for this problem is definitely going to be 0. That's the key to this problem. Okay, now at this point we have to solve for V. V is the terminal speed in the FD formula. Yeah.
So, say if you're like sky, this is like for the terminal velocity, saying how like you can't put the air can't push back on here. But if you're like skydiving or whatever, you're going from a lower density air to a higher density.
If the density is changing, then terminal velocity will fluctuate. It is held constant here though.
Okay.
And you're totally right. In a college level problem like this, you'll have density be a function of h, the height. So then you have to use calculus a little bit more than this. I don't see this being a problem on the AP exam with integration of the density function. It's not going to happen. So, but that is absolutely right what you're saying. Yep. All right, so we've got mg for this first part. Mg sine theta minus mu k. What's Fn equal to in this problem? What is Fn equal to, Chris?
FG cos theta.
Thank you. Fg cos theta is really Fn. Where is he getting that from?
The free body diagram.
Yep, the free body diagram. Look at the y direction. We're smart enough now in this course. We don't need to think about like as if we were juniors. Look at what I just circled there. That pretty much tells me there is an equilibrium in the y direction because there's no acceleration off of the ski ramp. The skier is not doing one of these while he's skiing at all. The skier is just coasting down, right? So there's going to be no vertical acceleration. So Fn is balanced by Fg cosine theta. So instead of putting Fn right here, I just placed mg cosine theta in its place. Right? We want to save time on an exam, so think about how we would approach this. So you guys are smart enough that you don't always have to write the y direction if you can see what's happening there. And now, what was I forget honestly the formula for FD. Was it 1/2?
FD is 1/2 C rho AB squared.
Thank you. And then just solve for V. Okay, everything else is known. I'm not going to continue going through it, right? We have all the other values.
Could we abbreviate the C rho A as just K when we're doing these, or would you prefer us?
You absolutely can, and on the AP exam, you probably would. I don't think they're going to go into depth about these three parameters in the exam, so they're most likely going to call it minus kb squared. They're not even going to put the 1/2 there, because the 1/2 is also a constant. So this whole thing can be lumped together as a constant if we assume that the drag coefficient isn't changing, the density, as Matt asked, isn't changing, your cross-sectional area isn't changing if you're not moving and turning. But if you're skiing and you do this, now it changes the ballgame completely, right? Look at the difference in your cross-sectional area that the wind hits versus this. My fiance loves this show, The Bachelor. Have you heard of it before?
Yeah.
Okay. Sorry if you love it. I hate it, but it's okay. I watch it with her. She wants to watch it. I don't watch it. I do physics. And she watches it. I sit there, honestly, I do physics, and she wants to be like, oh my god, yeah, that's great. So the other day, there's this scenario, and the only reason I liked it is because they were using wind force, and I was like, oh, this is kind of cool. It's physics. So whatever. These girls are all competing for this guy's love, which is ridiculously terrible, and they're trying to go through an obstacle course. And in the obstacle course, they're like running, and he's a pilot, the guy in the show, I guess now. So they have this like giant fans, which pretty much create like a wind tunnel in a sense. And they're running, and all the women pour, they feel terrible. They've got like a lubricant on the ground too, so they're slipping. They're like falling and stuff, and it sounds terrible. Right? People love this show, I know. So anyway, the point is, the guy was watching it all happen, and he was kind of like laughing at one point, but what he did was this. It was very interesting. I thought to myself, oh, this is physics. He doesn't even know what he's doing. Maybe he does. He's a pilot. So if you were to stand right in front of the fan, you have a lot of cross-sectional area, right? And the fan's going to blow you back. And when the girls were running, they were just running like this, and the air, whoosh, they would slip, right? And it was really funny to watch, but it was terrible. He instead was walking forward like this. His body was at this. The wind is coming this way. He walked toward the fan like this. And then eventually one or two of the girls realized to duck down kind of and lower themselves. Why? Exactly. Decrease your cross-sectional area. And literally, that's by him doing this and leaning like this, his cross-sectional area is no longer this much. It's a projection of it. Think about like the y component of the hypotenuse, right? This is the y component. His cross-sectional area is now the y component of his actual area itself. So it's A times the sine of theta. So if he was angled down at 20 degrees from the ground, or they say 70 degrees because it's the other way, it would be A sine theta, and therefore it would be a lower value than A because sine theta is less than 1. And eventually a couple of the girls literally noticed the same thing, and they were like almost doing like an army crawl to get lower than graph's theta.
So like if hit by him lowering his like cross section, he's reducing his like whatever it is, reducing the cross section. But like if you were like to like duck your head so the air had an easier time moving over, you would
that would change C. C is the drag coefficient. So if your body was more streamlined, that's changing C there. I mean, it's also changing A inherently. They're very related to each other. But C has to do with the contour of the body itself. Does that make sense? Okay, so like an airfoil for a plane, they're contoured in a way so that the airflow is nice and.
Yeah, that's us. Cause that's like you're like hinged at the hips, like your hips are high at the highest point of your body, but your head is like kind of like tilted upward.
Something like that almost,
Yeah.
and going forward into it. Yeah, the air would be flowing off your head versus off your body. It may change the C value as you do that as well. Yeah. Okay. Tara, Diane, then I'll go to you guys.
Yeah. So part B of this problem says something about the derivative of C. Are we expected to?
Can you just read it real quick?
Yeah.
I'll recall what it
It
says.
if a skier can vary C by a slight amount dc by adjusting, say, the hand positions, what is the corresponding variation in the terminal speed?
Okay, so it asks you if you can vary C by doing what is it? What is the phrase?
By a slight amount DC.
Adjusting
It's
say
just
the
like
hand
plugging
position.
in the other formula.
I mean, or you could just look at like.
What's the final solution for part A? It's not to be generic. Can we get it?
Root 2mg times sine theta minus.
So you gotta hold on. Let me write it down.
I'm still on.
Root 2mg. What do you get?
Root 2mg times sine theta minus mu k cos theta.
No.
And the sine theta and mu k cos theta are in parentheses.
Is this what you're saying right here?
Yeah, I took out the 2mg.
I got you. You factored it out of everything?
Yeah.
Because you moved that over and multiplied by 2?
Mm-hmm.
Gotcha. So like that?
Yeah.
Okay. And then it's all over row VA. Okay. Yeah, that makes sense. Okay. So the question was if you can vary C by some small, infinitesimally small value dc, the differential of C, dc. You guys, right? dy dx, differentials. So if you're changing it here, what would happen to V as a result? If there's a change, it would change.
In 1 over the square root of C. DC.
Where is that coming from?
Or 1 over the square root of D. Because if you plug it in front and then take it out, then that's what it's equal to.
Yeah, so what you're really doing is replacing this with DC, and then you're taking the square root of that value. So it's indirectly related, right? The two of these things. So if DC is a positive change and this goes up as a result, this will go down. If DC is a negative change, this will go up. But not by the direct value, but by the value of 1 over square root of DC. Because it's underneath a radical here. See how that's under a radical? So if I change this and I doubled it, it would now be changing by a factor of 1 over root 2. If I tripled it, changing by a factor of 1 over root 3, etc., etc. So it wasn't really a calc problem, but the idea is about change, and they're trying to involve calculus because the text is a calculus text, physics book. But it wasn't really needed to take a derivative there. Okay.
So is the shape of an airplane wing, does that make C really, really small? So that there's very little?
Yeah.
platform?
When it's okay. So here's the thing, Max. That's a good question. Max, do you know this one? Your parents are both pilots. That's why I asked.
Yeah.
He said, does the shape of the airfoil, the wing airfoils, cross-sectional shape? By the way, it's like a teardrop. Have you guys ever seen a cross-section of an airfoil? That's what it looks like. Okay, the air flows over the surface like this, and flows here.
Does it have a little lip on the bottom so the air captures?
There's a couple, there's like little flaps that can come out of the bottom. These are little things that can alter, they can change angles. But the concept is that when it's in this position, you create more lift below than you have drag pulling it down. So this creates lift off. Now, as a result, it is very streamlined. The C value is very low, therefore reducing FD. When you turn the flaps like this though, suddenly you're changing the cross-sectional area and the C value both. Because now the air is not streamlined and flowing over the surface of it. So the lump parameter K would change for sure when the flaps alter, when you're coming down on the landing. Okay? But it's both C and A in that problem. It's not rho. Rho would only change as height changes, because that's air density. All right, good question. I saw a couple other hands up. Did that answer most questions of this one? Okay. What else do you guys want to do? No. We've got 3 other problems. We've got the free response I sent you. Just give me something that was really like bothering you or you were struggling with. I'm going to try and pull them up on here so I have the wording for them to make it easier. Yeah, go ahead, Matt.
I was like really confused by I had a few people explain to me, and I was really confused by the number. I was like, I leveled up 8 on the versus raise a graph question.
What year was it? Does it have a year?
Let me find it.
2009.
Yeah, 2009 BB1.
2009 BB1.
Yeah.
Yeah.
Hold on.
Oh yeah.
2009.
Yeah.
You know what? I'm just gonna copy it from right here. I have it right here anyway.
That's 2 decades.
2009 BB1. You said okay. Come on.
Max peaked in 2009.
How close? It was the second to last problem. You said. Right here.
Yeah. Like after Alex explained it to me, like he didn't like the I kind of understood the concept of it, but like still when I went back and tried to redo it, yeah, I still
Okay. And then what's the next part? Plotting. And then find the value of g. Okay. All right. Let's run through this whole problem. Does anybody? Well, you tell me, guys, first. So you went over. Some of you went over with Alex that were there. Some were not there. Some were there the whole time. I know. So did he go through the actual solution with you at least already, or did he just step you through what he think? I'll do it then. Okay.
Yeah, 'cause there are like different ways you can do it apparently, like different things you can graph.
Oh yeah.
Let me start with this. So let me just read real quick. An experiment is performed using the apparatus above. A small disc M1 on a frictionless table is attached to the end of a string. The string passes through a hole in the table and is attached to a narrow vertical plastic tube. An object M2 is hung at the other end of the string. A student holding the tube makes the disc rotate in the center with constant. So this is the lab we all did last year. You remember this, right? Okay, the general idea of the lab, obviously. Now, what changes about this is that there's now what? Constant radius R. Any friction involved? None? Makes it actually easier. I thought it was going to add friction. Okay. So a student holding the tube makes it rotate while another student measures the period P. Derive the equation P equals 2 pi root M R over M2G that relates P and M2. Okay. So you're trying to find the time. The time is going to play a role in the velocity when you use the overall equation. Because the velocity is going to equal what? The circumference over the time. Let's make that clear again. I mean, I spent I think 20 minutes one day talking about periods of revolution because this test has a tendency to use that term. They love using the period of revolution.
On the sentence one, every single circular motion problem.
They gave you the period, right?
They don't give you T, they don't give you periods.
They say again?
They didn't give you single T values, all period values. Or
That's what I mean. They didn't give you the actual, they didn't give you the velocity, for example, the tangential velocity. They'd give you the period, which is really the time it takes, and then you have to divide that into circumference. So remember, what is the distance traveled? The distance traveled, or the period, is equal to, in this case, the time. Oops. Okay. The time is equal to, in this case, velocity over, length over velocity in this case, right? Distance over velocity here. So the period is going to equal, in this case, 2 pi r over the velocity. So I think we're going to need to find the velocity and plug that in somewhere. So I'm going to also put that down. Okay, so I'm going to have both, and it's P, not T, sorry. It's P. Okay. So these are relationships we're going to want to write right away. Okay, the velocity of this object, or average speed really, equals distance traveled, circumference, over time period, which is P. Then switch these two, you get this one right here. So we're going to use some of this in the actual value. So now we have to also then ask ourselves, what is our equation of motion here? So how are we going to figure this out? What are we going to analyze? Are we going to analyze mass 1, mass 2, both? What do you think? Chris? Probably both. It would probably help, right? So if I look at mass 1, when I draw my free body diagram for mass 1, I'm going to draw a bird's eye view. I'm not going to draw it as seen on the diagram. I'm going to draw a bird's eye view of mass 1. So here's mass 1 right here on the edge. And here's the path that it's taking. There we go. And here's the path that it's taking on the there we go. So mass 1, we know, is being pulled toward the center. By what?
Gravity.
No, not. Be careful. What is it directly being affected by? Not gravity. Tension. What is causing tension of mass 2? Again, mass 2 is pulling down on the rope, which is causing tension in the rope. Keep that in mind, please, here. There is no gravity of mass 1 affecting this problem at all. The vertical direction for mass 1, which is really out of the page, is Fn. Into the page right now is Fg. Imagine this is on a table spinning in front of you. Fn pushes up, Fg pulls down. That is not acting in the center of the circle at all, right? It's acting up out of the circle. I shouldn't even use the word out. It's acting up perpendicular to the circle and down perpendicular to the plane of the circle. But the only thing acting toward the center here is the tension from the cable, which is transmitted via the weight of M2. So when I look at the free body diagram for M2 right next to it, I know that tension pulls up, and I know that the weight pulls down.
Since the radius is a constant, would you be able to say that Ft equals like mtg?
Absolutely, and that's yeah, because the radius is constant, because it's not accelerating up or down.
If it was varying, then it would.
Very good. So ready? You spin it faster. What happens to the mass hanging? It starts to slide up. You slow down, slow down, slow down. Not enough desire to move outward, centrifugal effect, not enough of it. So therefore the mass will start to slide down. So if this mass here were sliding either up or down, it would have acceleration, and we would say Ft minus Fg2 equals ma. But it's not moving up or down, because the radius is a constant in this problem. That's the only reason it's not sliding up or down. So as a result, Ft minus Fg2 equaling m2a, well, that's going to go to 0. That's your equation of motion right there for the second mass. That helps us because now we know that the tension in the cable is equal to the weight of the second mass. I'm going to use this over here with the first mass in a moment. So this is very useful because it's going to be one of our variables that we're going to need for the first mass. For the first mass, we know that we say whenever something is moving in circular motion, the sum of the forces acting toward the center equal mv squared over r. This is always the case for circular motion problems. So the equation looks slightly different. It's no longer just ma, because a is v squared over r. What force is acting toward the center in this problem? Tension only. And toward the center, we said, is considered positive. We've been considering toward the center as positive. And that equals mv squared over r. As a result, since Ft is really Fg2, we can plug that in right over here. So let's take Ft and replace it with m2 times g, because the weight of the second object is just mass times gravity. So this next part becomes m2, and this was m1, by the way. This other one was m1. Over here, please look. This was m1, this was m1. Because the object spinning in a circle is m1, which is why we're calling that m1, because this is the part that's spinning in a circle. We're going to recognize here that we have m2g equals m1v squared all over r. And then the final thing we have to do is recognize, well, look at part A. I know it's hard to see. Part A does not have velocity in it, right? But we do. We have velocity. So there's a good chance we're going to substitute for velocity. And what will that give us? Well, look, that's velocity right there. So plug that whole thing in. Doesn't that introduce P suddenly? And therefore allowing us to solve for capital P. Okay, that's the last step in this process for part A. So this becomes m2g equals m1. I'm running out of room on my screen, sorry. And m1 times v squared. V squared is really 2 pi r over p. So now it becomes, you got to solve this equation for p.
No, you have just 2 pi r p squared.
Squared, thank you, squared. I put the parentheses, not the squared. You have to solve that equation. There's a squared on the outside there. Thank you. So multiply by r, divide by m1, square this whole thing, rearrange, you will get that equation they listed on top. Okay? All right, that's part A. Part B, or after part A, it says, the procedure is repeated and the period P is determined for 4 different values of M2. Okay. So M2 is what they're changing, I see it, all right. Where M1 is 0.012 and R is 0.80. The data which are presented below can be used to compute an experimental value for G. An experimental value for G. Okay. So we're trying to figure out what G is in this problem. So what we want to do here is somehow make G, let's see, our slope. We can use that for the slope in this. So let's see what it asks for part B. What quantities should be graphed to yield a straight line, with a slope that could be used to determine G? All right. So this is where it's going to get a little bit tricky. So what you want to do is recognize first, we have the equation. So even if you didn't get part A right, you should use the solution for part A. Do you see what they do in this problem on purpose? They're not asking students to get the solution for P. They're saying derive and prove that equation. Why are they doing that? So that you can still do part B. Is that clear what I'm saying right now? So if you really couldn't get part A, you could absolutely still do part B. So we want to recognize here that we want to plot really P versus something. That's what we want to plot. P versus something. And really in this problem, the value of P is a function of the mass. Of the second mass. It changes each time. But we want to calculate G as a result of this with all the others held constant. So what can we do for a problem like this? If we want it to be a straight line and M2 is in the denominator there, what we really want to do, let's see, let's plot it with, here, it's going to be P equals, the 2 pi is definitely in front. You're going to have M1 and R constants. You want to have G as your slope. So let's put G here for a moment. And then this is going to be a 1 over M2. You see what I'm doing right now? I'm taking everything out that's not M2. Because M2 is what's varying. This is Y and this is X right now. So this is Y and this is X. So what is this whole thing? What is this whole thing?
That's our M.
This is your slope. Very good. This whole thing is a slope right now. So what would we have to do? We would have to get rid of this whole thing and somehow get G to be the actual constant for a slope itself.
M1 and R are constants, you can turn that into
You can get numbers, yeah. So you can plug in value. These are constants that are given, so you'll get a constant for this as a value. And then what you want to do is plot P versus this whole thing right here. So you're not going to use these as the x values. The x values are going to be 1 over this value under the square root. Okay, it's going to be 1 over this value under the square root will be your different x values that you're going to change. And then you're going to have to solve for G by getting the slope of this. So you can get a slope and then determine G. G does not have to be your slope, it turns out here. Okay, so if you plot P, which is this number, plug in 0.02 here in the denominator, get a value, divide through, you could solve for G with all those values.
I graphed 1 over P squared versus M2, and I got the same answer as people that.
Yeah, that'll work.
Yeah.
Because you're going to square both sides and putting M2 on the top, let's P in the bottom. That works. Yep, very good. That'll work also.
Can we have the lab do Monday?
Sure, that's fine. Guys, come in. I would benefit you for the test, so you know.
Just work on that. It's just
Today and tomorrow after school. Listen, if you finish it already, you want to turn in, I'm happy to give you like a bonus point or something, because some of you might have done it already. But Monday's fine. why they did that.
Yeah.
Smart, Chris. I like it. Good luck.